Okay, so this time I want to show you how to solve a 2D transport example, again using the method of characteristics. It's harder to draw the picture for this one because it's in 3D, so make sure you first view the video on 1D transport example because I'm going to just use the same idea there. So what was the idea there? We were saying that there is a curve xt, yt, t, where this left side, where this function u is a constant. So u of xt, yt, t will be a constant. Now what justifies us to say that? Well, that's because this side can be written as y comma negative x comma 1 dotted with the gradient of u. Sorry for changing the order. I'm really thinking of my coordinate system to be x comma y comma t. If the coordinate system was t x y, then I would put 1 here. But anyways, if this is what you have, then the gradient of u is ux, uy, ut. That's the gradient, right? So that's this. So if you do a dot product, you get y times ux, negative x times uy, 1 times ut, which is exactly this left side. Okay. And then saying that, oh, this is, if you divide both sides by the size of this, that's like the unit vector dotted with the gradient, which gives you the directional derivative. So this equation is basically saying that there's a direction where the directional derivative of u is 0. And I was explaining in 1D case that it gives you this characteristic lines where the function u stays constant over that line. Okay? So that's where this idea comes from. Okay, so as with the same idea as the 1D case, let's write down the dependence diagram of u with respect to t. U has a direct dependence on t, but u also depends on x and y, where those two functions depend on t, right? That's the dependence diagram. So if you wanted to know how u changes with respect to t, you have to write down all the ways that change of t gives you changes of u. So there's a direct influence, so you can think about how much u changes under changes in t. And then this is going through this way. Changing t will affect x, so there will be how much x changes with respect to t times, and then changing x will bring change in u, so there will be how much u changes with respect to x, and multiplying these two gives you how changes in t brings about the change in u going through this way. Okay? In the same way, there's also change of y with respect to t, and then u also changes with changes in y, and then you have some of these three things giving you the total change of u when you change the value of t. That's the multivariable chain rule that you learned in multivariable calculus. Okay, so now you compare this with this and say, oh, these two are the same, ux are the same, uy are the same. So if you had x prime equals to y, and then y prime equals to negative x, yeah, so since x is just a function of t, this partial derivative is really just a regular derivative, so that's why I'm writing x as x prime, round x, round t as just x prime. Same thing here. If these two things are satisfied, then this derivative will be exactly that one. So you can see that this condition would end up being this condition if these curves are chosen to satisfy this differential equation. Okay? All right, so let's solve this. Well, it's a system of differential equation which you learned how to solve in the ODE class, so I'm going to assume that you do know how to solve this. Please review that part. One easy way to do this would be just differentiate both sides by t, so x double prime will be y prime, but since y prime is negative x, you get negative x, and then you say, okay, what are functions which gives you negative of itself if you differentiate twice? Well, we know those functions are we know that those functions are cosine t and sine t, right? So what we can say is that x is in general c1 cosine t plus c2 sine t. So I'm taking a shortcut. There's definitely ways to get this by using eigenvalues, eigenvectors, and all that. Okay, but then now you have y. Y is the derivative of x, right? Y is the derivative of x. So you differentiate this and you get negative c1 sine t plus c2 cosine t. And then I want to further investigate this. Think about what x of 0 is. X of 0 is c1 times cosine 0, so it's just c1, plus c2 times sine of 0. Sine of 0 is 0, so this is what you get. So c1 is x0. And for the same reason, if you plug in 0 here, this will be 0, this will be 1, so c2 will be y of 0. So you also get c2 as y of 0. So that's what I'm going to do. I'm going to rewrite these in terms of x equals to c1. Instead of c1, I'm going to write down x0 cosine t plus, and then c2 will be replaced by y0 sine t. Y would be x0 negative x0 sine t plus y0 times cosine t. Okay, and I want to also rewrite this in terms of a matrix notation. It's going to help us later. Okay, so I'm going to rewrite this as cosine t, sine t, negative sine t, cosine t, x0, y0, just like that. Okay. So we've identified the flow lines. It's harder to draw because this is 3D, but this is where u stays constant. Okay, now what we're going to say is we want to ask the following. Take this equation and plug in t equals to 0. See what happens. You have u of x0, y0, 0 is equal to that constant. But if you look at this part, if you have x0, y0, 0, that should equal to fxy. That's your initial condition. But instead of x and y, we have x0, y0, so let's respect that. We're going to write down the right side as x0, y0. And because along the flow lines, the u does not change, you can say that this is now equal to u of x, xt, or x, y, and t. Right? So if you have a generic position in space, x, y, t, and you want to know the value of u, what do? You travel backwards through this flow line, and then you eventually figure out where it started from. You identify the initial condition, and that will be your value. You just fetch that value, okay? So now, what do? Well, so therefore, here's the problem. Now the problem is, given x and y and t, we have to figure out what their x0 and y0 is. Well, that's why I wrote this down, because, see, this matrix equation, if you solve it, it gives you x0 and y0 from x and y. Okay? And to solve this, all you have to do is just invert this matrix, right? If you take the determinant cosine squared plus sine squared, that's 1. Luckily for us, I intentionally chose this example because this determinant is 0, this determinant is 1. So when you invert this to the other side, you end up with these two switch, so it's cosine t, and these are negative, so you have negative sine t here, sine t here, and you multiply this to x and y, that gives you x0, y0. Okay? You should have 1 over determinant here, but the determinant is 1, so that doesn't count. So here's what you have. And this means that x0, so if you take this system and you solve for x0 and y0, you get x0 as x cosine t minus y sine t, and then y0 as x sine t plus y cosine t. Okay, so we're almost done. See, that the reason we wanted to know this is because I want to rewrite that. So if I plug these into this one and using this identity, here's the final answer, which says that u x y t, in general, the solution is the initial condition evaluated at x cosine t minus y sine t, and then x sine t plus y cosine t. And that's the solution. Now, just take some time to actually plug this solution into the left side, and you'll see that indeed this is going to satisfy the differential equation. And if you plug in time t equals to 0, you get f of x comma y. So it does satisfy the initial condition as well. So you do see that this is the solution of the 2D transport equation. Now, one more thing. What is this flow line? Well, if you think about the case when here's x and y, and then t is this direction. So if you think about the case when you start with 1 comma 0. So let's say at time t equal to 0, the x value was 1 and y was 0. Then if x value was 1 and y was 0, there will be cosine t comma, no, just a minute. Yeah, if x is 1 and y was, okay, so in that case, you're going to get cosine t and negative sine t because this is 0, right? So what that means is it's a circle that's going this way. Okay? So you see that you can kind of see that the characteristic curves are concentric circles where the center is at the origin. So you see that whatever it is, this function will stay constant over this direction. Okay, yeah. So that's something nice to think about.